Hello everyone. Today's story is about the life of Earth. We'll journey through time together, from the birth of the solar system to the formation of Earth and the Moon, the rise of oceans and life, the drifting of continents, the deep freezes of global ice ages, and the 5 great mass extinctions that shaped the planet. From there, we'll move into the age of modern humanity. And finally, we'll look billions of years into the future, at Earth's eventual death. Scientists estimate that Earth formed from the dust and gas of the primordial solar nebula about 4.6 to 5 billion years ago. That's an almost unimaginable span of time. So to make it easier to grasp, let's shrink the entire history of Earth into a single 24-hour day. On this scale, the Big Bang, the birth of the universe itself, about 13.7 billion years ago, would not even fall on Earth's birthday. It would have happened about a day and a half earlier, long before our planet even existed. About 7 to 15 minutes before Earth itself was born, the entire solar system came into being. That moment dates back roughly 4.567 billion years ago, when the sun ignited at the center of a swirling cloud of gas and dust, and the planets, including our Earth-to-be, began to take shape. The Earth's story begins hand in hand with the birth of the solar system. At first, there was no sun, no planets, no orbits, only a vast swirling cloud of dust and gas, slowly turning in the silence of space. This cosmic cloud was made mostly of hydrogen and helium, leftovers from the Big Bang, but sprinkled among them were heavier elements, iron, carbon, and oxygen, born in the fiery depths of the ancient stars long before our own world came to be. Let's rewind to that moment, roughly 4.6 billion years ago. Somewhere in the galaxy, a massive star reached the end of its life. It exploded in a supernova so powerful that it scattered its ashes, interstellar dust and gas, across the cosmos. Over time, gravity pulled that debris together again, forming what astronomers call a molecular cloud. As the cloud collapsed inward under its own weight, it spun faster and faster until it flattened into a giant cosmic whirlpool. At its center, matter piled up, grew hotter and denser, until atoms themselves began to fuse together in nuclear fire. That was the birth of our sun, a newborn star blazing into life. Meanwhile, baby Earth was also on the way. When the sun ignited, its powerful winds pushed much of the lighter gases outward. The remaining dust grains began to stick together, forming clumps, then larger fragments, and finally, planetesimals, small building blocks of planets. These collided again and again, growing larger with every impact. Close to the sun, the heat was intense. Hydrogen, helium, and other volatile elements were blasted away, leaving behind heavier materials: iron, silicon, magnesium, sulfur, and their oxides. These became the dense rocky terrestrial planets: Mercury, Venus, Earth, and Mars. Farther from the sun, where it was cooler, volatile elements could condense and remain. There, giants of gas and ice, Jupiter, Saturn, Uranus, and Neptune took shape, built mostly of hydrogen and helium with only small, dense cores deep inside. And so, from fiery explosions, swirling dust, and countless collisions, the solar system we know today was born. Rocky worlds circling closest to the sun, and colossal gas giants keeping watch in the outer reaches. The stage was set, the lights turned on, and Earth, our small rocky planet, was ready to begin its journey. At exactly 0 hours, 0 minutes, and 0 seconds on our cosmic clock, Earth was born. That moment, around 4.55 billion years ago, marked the beginning of our planet's long and extraordinary journey through time. The story of Earth begins here. At this moment in deep time, a brand new world had just been born, what scientists call the proto-Earth. But here's a twist. Proto-Earth may not have been alone in its orbit around the Sun. Astronomers suggest that another young planet was forming nearby, sharing Earth's path around the Sun. This mysterious world has been given a name, Theia. Roughly the size of Mars, about 1/10 the mass of Earth. Theia circled the step of our planet, locked in a delicate balance point known as a Lagrange point. For a time, two worlds danced together, but balance never lasts forever. One day, the inevitable happened, a collision of unimaginable scale. When Theia slammed into proto-Earth, it was an impact far greater than the asteroid that would later wipe out the dinosaurs. The explosion blasted colossal amounts of rock and molten metal into space. If you could have stood on the surface back then and looked up, the sky would have been filled with glowing arcs of debris, rings of shattered rock, like Saturn's, circling above a wounded young Earth. And yet, Earth was not destroyed. The angle and speed of the collision weren't enough to tear the planet apart. Instead, much of Theia's metal core merged with Earth's, sinking deep inside to become part of its dense, iron-rich heart. Meanwhile, the scattered fragments of the Earth and Theia slowly began to gather. Within about a year, gravity pulled them into a new, shining companion, the Moon. This idea, known as the giant impact hypothesis, is the most widely accepted explanation for the Moon's birth. It not only explains why Earth has such a dense core and why the Moon forever circles our world, but also why Earth tilts on its axis by 23.5 degrees, giving us our seasons. Without that fateful collision, there might be no spring or autumn, no long summers or winters. The crash also sped up Earth's rotation, setting the stage for the restless shifting of tectonic plates that would one day raise mountains and open seas. From the destruction came creation. From chaos, a planet and its moon were born. At 2 a.m., on Earth's 24-hour clock, about 3.8 billion years ago, the oceans formed, and with them, life itself began. From the swirling seas, the first living cells emerged, tiny sparks of vitality in a vast ancient ocean. In Earth's earliest age, known as the Hadean Eon, our planet was nothing like the blue-green world we know today. It was a true hellscape, a molten sphere wrapped in choking clouds of toxic gas. The air was thick with methane, carbon dioxide, and hydrogen sulfide. There were no oceans, no oxygen, no hint of life, only fire, dust, and chaos. But time is a patient artist. Over hundreds of millions of years, the bombardment of asteroids slowed, the surface began to cool, and magma started to harden into the first fragile crust. Heavy elements sank to the core, lighter ones floated upward, shaping Earth's layered body. To us, that crust would have looked solid, but in truth, it was as thin as an eggshell on a cosmic egg. Beneath it, the planet still boiled with molten rock. And then came the water. At first, it existed only as steam, trapped in the scorching air. But as Earth cooled below water's boiling point, the vapor condensed and fell as rain, an endless deluge that lasted for millions of years. Imagine skies dark and thundering, rains pouring without pause, carving rivers, filling basins, and slowly gathering into vast, primitive seas. Meteorites and comets delivered even more ice and water, adding to the flood. These early oceans were smaller than today's, holding barely 1/10 of the water we now see, but they were enough to change everything. These primordial oceans were not just water. They were strange, chemical cauldrons rich in organic molecules. There was no protective ozone layer in the sky, so ultraviolet radiation poured down onto the surface. Lightning split the clouds, volcanoes erupted endlessly, cosmic rays showered from above, and meteor impacts rocked the atmosphere. All of these forces became energy sparks, powering chemical reactions that stitched simple compounds, methane, ammonia, and carbon dioxide, into more complex molecules, amino acids, sugars, the very raw materials of life. Storm after storm washed these molecules into the seas, creating what scientists often call the primordial soup. Over time, these organic ingredients grew richer and more varied. Protected from destruction by sinking into deeper waters, something extraordinary was brewing. And then the great mystery. Somewhere in the ocean broth, one molecule gained a power unlike any other, the ability to copy itself. This replicator was the seed of life. It wasn't DNA yet, but it was the ancestor of all genetic material. It could replicate, sometimes making mistakes, mutations. Some mistakes made it weaker and short-lived, but others made it stronger, faster, more efficient. The successful ones multiplied, competing for resources, evolving even in the earliest forms. These replicators eventually found homes inside bubbles of fat-like molecules, the first primitive membranes. These fragile protocells offered protection and organization. Within them, chemistry became biology. Over time, RNA, DNA, and proteins each took their roles. One to store information, one to copy and transmit it, and one to speed the reactions of life. About 3.5 billion years ago, Earth hosted its last universal common ancestor, also known as LUCA, a simple, single-celled organism with a cell membrane, ribosomes, and DNA, but no nucleus or complex structures. From LUCA, all living things trace their family tree. Bacteria, plants, animals, and eventually us. What began as storms, fire, and a rain of cosmic debris had given birth to something entirely new: life. From molten rock to rain-soaked seas, from molecules to cells, Earth had crossed its first great threshold. The stage was set for the long, winding story of evolution. By 5 a.m. on Earth's 24-hour clock, about 2.4 billion years ago, the planet entered a dramatic turning point, the Great Oxidation Event. Tiny microbes had been quietly releasing oxygen for millions of years, and now the atmosphere began to fill with it. What was once a deadly poison to most early life forms became the foundation for the world we know today. But this oxygen surge also triggered catastrophe, plunging Earth into the Huronian Ice Age. Vast sheets of ice spread across the planet, one of the Earth's global glaciations in Earth's history. By 2.4 billion years ago, the age of Archean was drawing to a close. Life in Earth's early oceans was still simple, made up mostly of anaerobic microbes, heat-loving archaea, sulfur-eating bacteria, and methane-producing organisms. These creatures thrived in a world with no oxygen, because oxygen to them was poison. Then, a revolutionary newcomer arrived: cyanobacteria. Despite the name blue-green algae, they weren't algae at all, but primitive prokaryotes with an astonishing ability: photosynthesis. For the first time in Earth's history, sunlight was harnessed to turn carbon dioxide and water into sugars, with oxygen released as waste. That oxygen, however, was catastrophic for the old order. Anaerobic life forms, unadapted to this toxic gas, began to die off in droves. Meanwhile, methane, a powerful greenhouse gas, 25 times stronger than CO2, was broken down by cyanobacteria. With methane stripped away and CO2 left behind, Earth's climate collapsed. Temperatures plunged. The planet tumbled into the first great deep freeze, the Huronian Ice Age. For nearly 300 million years, Earth was entombed in ice. Its average temperature dropped to around -50 degrees Celsius. Oceans froze, continents vanished under glaciers, and life teetered on the edge of extinction. Yet, paradoxically, this apocalypse laid the groundwork for everything that followed. As oxygen levels rose, some of it transformed into ozone, creating the first protective ozone layer high in the atmosphere. For the first time, ultraviolet radiation from the sun was blunted, allowing life to creep closer to the ocean's surface, and eventually, one day, onto land. Geologists call this turning point the Great Oxidation Event. But oxygen was more than just a shield. For some organisms, what was once poison became a superpower. A few microbes evolved ways to harness oxygen for metabolism, unlocking vastly more energy than fermentation ever could. These were the ancestors of all aerobic life, including us. It was during this time that one of the most profound partnerships in the history of life occurred. A small bacterium, not unlike modern relatives of parasites such as rickettsia, found itself swallowed by a large host cell. Instead of being digested, it survived, even thrived inside. The little bacterium used oxygen to process waste and generate energy, some of which benefited its hosts. Over time, the partnership deepened into full symbiosis. The bacterium became a permanent resident, the mitochondrion, the powerhouse of the cell. A similar event later happened when photosynthetic cyanobacteria were absorbed, giving rise to chloroplasts. These endosymbiotic mergers produced the first eukaryotic cells, larger, more complex than their prokaryotic cousins, and capable of astonishing innovation. By 7 a.m. on Earth's clock, around 1.8 billion years ago, the planet saw the birth of its very first continent. This marked the beginning of Earth's long history of drifting, colliding, and reshaping continents, a process that continues even today. After ages of molten chaos, shifting crust, and endless volcanic activity, solid land finally rose above the global seas. The eukaryotes were spreading across Earth's oceans, while on the surface, land masses were shifting. Vast supercontinents began to form, with Columbia, also called Nuna, among the earliest known, uniting much of Earth's crust into a single gigantic landmass. What began as a crisis, toxic oxygen and a frozen world, ended as a transformation. The Great Oxidation Event not only reshaped Earth's atmosphere, but also rewired the very machinery of life. It paved the way for complexity, for multicellularity, and ultimately for us. After Earth's dramatic recovery from the Great Oxidation and the endless ice, our planet entered what geologists sometimes call the most boring billion years. For nearly a billion years, little seemed to happen on the surface. No mass extinctions, no great bursts of new life, just a slow, steady hum of biological and geological activity. But beneath this apparent monotony, the stage was being set for the next great leap forward. Continents drifted, collided, and stitched themselves together. By around 1.1 billion years ago, the landmasses of Earth fused into what may have been the largest supercontinent ever to exist, Rodinia. Imagine a single, massive landform dominating one hemisphere of Earth. Its coasts battered by waves, its interior a barren desert. At this time, the ozone layer was still thin and incomplete. Without its protection, ultraviolet radiation poured down in lethal doses, making the land nearly uninhabitable for life. Meanwhile, in the oceans, life was quietly diversifying. Archaea, bacteria, and eukaryotes each continued to evolve, branching into countless lineages. Most organisms were still single-celled, but some began to form colonies. With primitive divisions of labor, outer cells protecting inner ones, inner cells specializing in reproduction or nutrient storage. These loose alliances were the first step toward multicellularity. By about 1 billion years ago, the first true multicellular plants, like green algae, appeared. Not long after, around 900 million years ago, the first multicellular animals followed. They were simple, perhaps sponge-like, with cells that could rearrange and rebuild if torn apart. But with each new experiment in cooperation, cells became more specialized, more independent. No longer could a single cell survive alone. The first fragile threads of complex life were being woven. At 10 a.m. on Earth's clock, about 770 million years ago, the planet plunged once more into an ice age. Vast sheets of ice stretched across the surface, freezing the oceans and transforming Earth into what scientists call a snowball Earth. Life clung on in the oceans beneath the ice, enduring one of the most extreme climates our planet has ever faced. For millions of years, Earth was a glittering white marble drifting through space. Life clung on only in scattered refuge, near deep sea vents or beneath thin layers of ice where liquid water remained. At last, after nearly 200 million years, volcanoes belched enough carbon dioxide into the atmosphere to tip the balance. Greenhouse warming shattered the frozen grip, melting the global glaciers in a cataclysmic thaw. Oceans roared back to life, climates warmed, and ecosystems once again flourished. By this time, Rodinia itself was breaking apart. Its fragments drifted and regrouped into a new arrangement, the supercontinent Pannotia, also called Nena. The world was on the brink of transformation. The deep freeze had tested life's resilience, and the splitting of continents reshaped Earth's geography. Both changes that would help set the stage for the astonishing explosion of life yet to come.